Hi, this is Dr. Rosario, and in this lecture we are going to be talking about the dissociation of water. What that means is our water molecule, our H2O, can dissociate into a molecule of hydroxide and a hydrogen ion. And we're going to be talking about that in our lecture today. Before we get into the details of pH and understanding the dissociation of water, we need to first do a review of some important math concepts.
So I'm going to go over three topics. I'm going to go over scientific notation, multiplying and dividing exponents, and then finally we're going to talk about logarithms. Okay, so scientific notation. Scientific notation is just a tool that we use to write numbers in a more manageable form. So what we do is we take a number and we write that number as a value between 1 and 10, and then whatever that is multiplied by a factor or power of 10. So for example, it's easier to understand this if you see it in action. If I have a number like this, right, so 68 million, that is a big number and a lot of zeros. In scientific notation, the way that I would write this is I would write it as 6.8, right, that's a number between 1 and 10. And then I would count the number of places it took me to get to that 6.8. So 1, 2, 3, 4, 5, 6, 7. Right? And that's going to be my exponent. So it's 6.8 times 10 raised to the power of 7. All right, another example going the other direction. What if I had a number like this? 0.000095. All right. Again, I'm going to express this as a value between 1 and 10. So 9.5 times 10, and then the exponent here, we're going in the opposite direction. 1, 2, 3, 4, 5 places to get to that 9.5. So because we went in the opposite direction, my exponent's going to be a negative number. If my value is less than 1, my exponent is negative. So it's going to be 10 to the negative 5. Okay, so that's scientific notation. Basically what we're doing is we're taking a large complex number with lots of digits in it and converting it to a simple 2-digit number and then expressing that as a multiple of 10. Okay. The next topic is multiplying and dividing exponents. So if we're doing this scientific notation where we have all these exponents, it's important to kind of refresh your memory on how to multiply and divide exponents. So for example, if I have two numbers and they have the same base, so let's say I have 6 raised to the power of 8, and then I have 6 raised to the power of 4, and I'm multiplying those numbers together. So 6 to the 8 times 6 to the 4, that would be 6 to the 12. I could do this with something that has a base of 10, right? So let's say I have 10 to the 12 times 10 to the 6. All right. In that case, the number would be 10 to the 18 because 12 plus 6 is 18. I'll do one more. Let's say I have 2 to the 4, and I'm going to multiply that by 2 to the 2. My answer here would be 2 raised to the 6. Okay. So that's if we're multiplying exponents, but what if we're dividing exponents? It's just the opposite. So if I have two numbers, the key here is if they have the same base and we're dividing, we subtract the exponents. So for example, if I go back to the example I had up at the top, if I had 6 to the 8 divided by 6 to the 4, right? Then my answer would be 6 to the 4 because 8 minus 4 is 4, right? And then same thing if I have, I don't remember what I used, 10 to the 6th divided by 10 to the 3, right? 6 minus 3 is 3, so my answer would be 10 to the 3. If I had 2 to the 8 divided by 2 to the 6, let's just say, 8 minus 6 would equal 2, so my answer would be 2 raised to the 2. Okay, so that's where if we're dividing by exponents or dividing numbers that have the same base but different exponents, we just subtract the exponents. All right, finally, logarithms. Logarithms really are just a way of expressing a number or expressing the exponent of a number. So we really just look at log base 10. So log base 10 is what that's called, which on a calculator it'll just say the function will just be the log function. So the log base 10 is really just asking what exponent do I have to raise 10 to get to my number? So for example, if I say what is the log of 100, that equals 2 because 10 squared equals 100, right? Or if I want to know the log of 10,000, right? Again, we're doing this all in base 10. So 10 to the 4 is equal to 10,000. So that means the log of 10,000 is 4. The opposite is true. So let's say if I have a very small number, if I want to know the log of 0.00001. All right. Well, how many decimal places do I have to raise to or move my decimal to get to the value of 1? So 1, 2, 3, 4, 5, right, to get there. So it's 10 to the negative 5 equals 0.00001. The log of that number is negative 5. Right. So if the value of the number is less than 1, your logarithm is going to be a negative number. If the value of your number is more than 1, then your logarithm is going to be a positive number. It's just asking what is the exponent? How many places do we have to move our decimal point for our log base 10? All right, so now that we've talked about some of that basic math, we're going to go ahead and move on to the basic principles of pH. And first off, we need to talk about just water. Water by itself, nothing else with it. And pure water is H2O, right? 2 hydrogen atoms covalently bound to an oxygen atom. Now, occasionally, these molecules are going to break apart. One of those covalent bonds will break. And when that happens, we end up with one hydroxyl ion, or OH negative. And then we also end up with one hydrogen ion, or H plus. Right? And of course they're in equal numbers because if you put them together, that reforms water. And really that often is what happens because this is a reversible reaction. So the water molecule will break apart, you'll get your hydroxyl ion and your hydrogen ion, and then they'll come back together and reform the water. And more often than not, we're reforming the water. So this is a reversible reaction, but we end up with a much higher proportion of water molecules than we do of hydroxyl ions or hydrogen ions. In fact, the ratio is about 554 million water molecules to every hydroxyl or hydrogen ion that we get. So what that means is if you have just a beaker of pure water, the concentration or the molar concentration of hydroxyl ions is approximately 0.0000001 molar, or that's the same thing as 10 to the minus 7 molar. And the same thing will be true for our hydrogen ion concentration, because your hydrogen ion concentration is always going to equal your hydroxyl ion concentration in pure water. So again, that's 0.0000001 molar, or the same thing as 10 to the minus 7th molar. All right, so that's pure water, but what happens if you add something to that water, right? We've been talking about solutions. Now, a solution, right, is where you add a solute into our solvent. Our water is going to be our solvent, right? We have aqueous solutions in biology. So an acid is something where when you add it to water, it actually increases the number of hydrogen ions in that solution. So a great example of this is an acid called hydrochloric acid, which is just HCl, that when you put it in water, the hydrogen and the chlorine separate and you get a hydrogen ion plus a chlorine ion. That's going to increase the total number of hydrogen ions in my aqueous solution. Now, the opposite is true as well. So a base is something that removes hydrogen ions from a solution. So a great example of this is ammonia, or NH3. So NH3, when you put it in an aqueous solution, some of those hydrogen ions that are present in that aqueous solution are going to combine with that ammonia to form ammonium, or NH4 plus. All right. There are other bases that when they are dissolved in water, so a great example is KOH. KOH, when it is added to water, it dissociates, right, to potassium ions plus hydroxyl ions. And then those hydroxyl ions further will combine with the hydrogen ions in the water in that solution to form just molecular water. So again, the same net change, we're reducing the number of hydrogen ions. Now, something to keep in mind is that if the hydrogen ion concentration increases, then the hydroxyl ion concentration is going to decrease, and vice versa. If the hydroxyl ion concentration increases, the hydrogen ion concentration will decrease. In any given solution where water is the solvent, we can write this relationship out like this, where the concentration of your hydrogen ions times the concentration of your hydroxyl ions is always going to equal 10 to the negative 14. All right, so if we're talking just pure water, that's pretty simple. We can see that relationship. Remember, in pure water, your concentration of your hydrogen ions was 10 to the minus 7. The concentration of your hydroxyl ions was also 10 to the minus 7. When you multiply those two numbers together, you get 10 to the negative 14. That's pure water. Right. Now, what if I add a acid to my solution and I increase the amount of my hydrogen ions? Let's say instead of having 10 to the negative 7 hydrogen ions in my solution, after adding my acid, I go from 10 to the minus 7 H plus, molar H plus, to 10 to the minus 4 molar H plus. So I've increased it, right? Because 0.000001 is going to be less than 0.0001, right? That's what those two numbers are. So if I add acid, right, I go from that 10 to the minus 7 molar hydrogen ion concentration to a 10 to the minus 4. What then is going to happen to my hydroxyl ion concentration? Well, again, if my H plus is 10 to the minus 4, I multiply that by my OH negative to get 10 to the minus 14. Well, so now in order to solve for my hydroxyl ion concentration, I would take 10 to the minus 14, divide that by 10 to the minus 4. When you divide by exponents, again, remember, you subtract. So I would subtract minus 14 minus negative 4. So minus negative 4. You can't, if you have two negatives, they become a positive. So it's negative 14 plus 4, which equals negative 10. So my concentration of my hydroxyl ions here is going to equal 10 to the minus 10 molar. Right? Do you see how I did that? So my hydrogen ion concentration increased, right? It increased up here to this number, this 0.0001 molar, or 10 to the minus 4 molar, where my hydroxyl ion concentration now has decreased to 10 to the minus 10 molar, which is the same thing as 0.0000000. That's 9 zeros and then 1 molar. Right? So that's a much, much smaller number. All right, so again, that ratio is always going to equal 10 to the minus 14 if you multiply your concentration of your hydrogen ions times your concentration of your hydroxyl ions. This, again, is only for our aqueous solutions. Okay, so now this all brings us down to the pH scale, because this is starting to get pretty complicated, right? The pH scale simplifies all of this for us. Okay, oops. So the pH scale is where we take the negative logarithm of the concentration of our hydrogen ions. That is our pH. Now our pOH is just the opposite. It's the negative logarithm of our hydroxyl ion concentration. So it really just simplifies these measurements. So for example, in pure water, right, remember we know that the concentration of H plus is equal to 10 to the negative 7th molar, right? So the negative log of that number, or the pH, so pH is equal to the negative log of 10 to the negative 7 here. Remember, the log, when we take the logarithm of a number, we're just looking at what is that exponent here. What do we got up here, right? So now we have pH equals the negative of negative 7, right? Which two negatives equal a positive, so the pH of pure water is 7. And this is what we call a neutral solution, right? It's neutral because the concentration of hydrogen ions and hydroxyl ions, which we've already talked about this, they're equal to one another in pure water. Now, in solutions where the balance is not equivalent, that's now where we get into acidic or basic solutions. So I've got a little table for us. So here's our table of pH. The pH can range from 0 to 14, right? Again, we're really just measuring the hydrogen ion concentration in our solution. So if you have a pH of 0, that means that you have 10 to the 0 molar hydrogen ions, which 10 raised to the power of 0 is 1. Right? That would be a very acidic solution. Our 10 to the negative 7, that is a very basic, that's a neutral solution. And then anything that has a pH greater than 7 is going to be what we call basic. Again, you can see here, I'm going to highlight this in green, that as we get higher and higher in our pH, the concentration of our hydrogen ions is going down and down and down and down, lower and lower and lower and lower. All right, so now let's put this all together and look at some examples. Okay, so here's our first example. So how much more concentrated is the hydrogen ion concentration in vinegar, which has a pH of 3, versus baking soda, which has a pH that equals 9. All right, so we can shortcut this answer. I could do it in my head in about 3 seconds, but to give you how you get there, I'm going to go through the steps. So remember that the pH tells us that hydrogen ion concentration, right? So if my vinegar here, with its pH 3, then my hydrogen ion concentration is 10 to the negative 3, right? And then my baking soda, with its pH of 9, it has a hydrogen ion concentration of 10 to the minus 9. Okay, now to find out how much more concentrated vinegar is than baking soda, keep in mind that 10 to the minus 3 is really 0.001 molar, and that 10 to the minus 9 is 0.000000001 molar. To find out how much more concentrated the vinegar is than the baking soda, all I have to do is divide that 10 to the minus 3 by 10 to the minus 9, right? That's going to give us that fold difference. Well, remember, when we divide exponents, right, we subtract, as long as that base is the same. So here you have negative 3 minus negative 9. Well, two negatives are going to make a positive, so that's going to equal minus 3 plus 9, which gives us 6. Okay, so the difference is 10 to the 6th, right? That's my total difference. Or 1 0 0 0 0 0 0, or 1 million times more concentrated. So an easy way to remember this is that for each number in the pH scale, that represents a multiple of 10. So if I have my pH equals 3, I know that that's more concentrated. That's more concentrated than my pH of 9. The shorthand is just to go, all right, well, 9 minus 3 is 6, so 10 to the 6th times more. Right. Every number of the pH scale represents 10 times more or 10 times less hydrogen ions in solution. All right, now the one last thing I wanted to mention was buffers. Now buffers, they're important because they maintain a relatively constant pH. Now that does not mean a neutral pH, it just means a constant pH. So for example, baking soda with its sodium bicarbonate is actually a really good buffer. It's a good buffer because it's a weak base. Don't worry about what that means for now. But what it means for you is that if I add acid to a buffered solution, the pH doesn't immediately go down. Instead, that buffer molecule kind of acts like a sponge to suck up the extra hydrogen ions. It absorbs the H+. On the other hand, if I add a base, to that buffered solution, then the buffer will release those hydrogen ions. And that again helps to maintain that relatively constant concentration of hydrogen ions in that particular solution. This is important, particularly in biological systems, because a constant pH is necessary for cells to function. So most cells, the cytoplasm is about a pH of 7. It's about pH 7.2. And that's because biological molecules, their shape is influenced by pH. Again, those biological molecules are sitting in an aqueous solution. If you change the pH, you change the shape of that molecule. And remember, shape determines function. So if you change the shape of that molecule because you've drastically altered the pH of the solution, then you have a problem because now your molecules are no longer functioning the way that they should. All right, so that's really why we care about buffers in this class, and we're going to talk about that a little bit more when we talk about our enzymes. All right, so I think that's it on pH and how to do some of these real simple calculations. I'm going to put up a few sample questions for you to try. Go ahead and practice those. Again, don't overstudy this. It's not going to be a huge portion of your exam, but do, check your knowledge. Make sure you understand it. All right, good luck.